Okay. Welcome. So we're going to get started now. Just a couple of announcements. If you would prefer to avoid the rough and tumble handing in of the homework at the beginning of lecture, you should also feel free to come by office hours Monday and hand them in then if you're done. That's just an option in case you prefer that. Also, next week, and I'll send out, you don't need to write this down, I'll send out a announcement about this, but next week we'll have the star party, which is the kind of required astronomical observing part of the course. There'll be a question on the homework 5, which is the one due later, not next week, but the following homework. The question won't be some complicated thing. It'll be something of the form, what did you see and what did you learn? So something rather generic. But this is required, so just to kind of have that on your schedule. I'll send out an email and I'll send out the information about how to look for fog to figure out if the star party is called off. Okay, so now we've talked a little bit about the formation of stars, planets in the solar system. We've understood a little bit about how the Earth works and about the broad geological and biological history of the Earth. What we're going to talk about over the next few lectures is really try to start to understand where did the basic building blocks for planets and life come from? Where did all of the elements in the periodic table come from? And most of that has to do with understanding the internal workings of stars. You can think of this by analogy to Charles's lecture on how the Earth works. We're now really trying to understand how stars work. And in doing that, we will understand the origin of most of the elements in nature. There are a few exceptions. A few of the lightest elements, hydrogen and helium, are produced actually in the Big Bang. We'll come back to those later. So what we're going to talk about today is a little bit of an overview of what the properties of stars are and how we know them, what actually powers the light that we see from stars, and why this was such a puzzle, in particular in the late 19th century. And then at the end, we'll kind of transition into our thinking about fusion as the energy source for stars by talking a little bit about the properties and nature of matter. So to remind you, stars like the sun are all, we think, large, basically spherical balls of gas. They're mostly made of hydrogen and helium, and the way we know that is something we'll get to a little later in this lecture. In a picture like this of the night sky, the stars look incredibly closely packed together, but we know now that that's actually an illusion, that stars are actually separated by huge distances, many, many light years, which is much larger, for example, than the size of a typical planetary system like our own planetary system. So even though this image gives you the impression of stars very closely packed together, that really is an illusion. Most of space is not filled with stars. Yep. So L, remember, is the power. It's like the watts, the energy per time flowing out of a star.
L is the luminosity.
L is the luminosity, exactly. Yep, thanks. And so stars have this commonality in being big spheres of hydrogen and helium, but they differ in exactly how big they are, how much they weigh, how bright they are, how much energy is generated by fusion and is leaving the surface, and in what the temperatures of the surface that we can see is. And how do we know these properties? Well, we've already talked a little bit about how we measure masses of stars. In the case of our own sun, it's the orbits of the planets around the star. In the case of other stars, we can measure their masses when two stars orbit around each other. Many stars are actually not isolated single stars. They're binaries, two stars orbiting around each other, and we can use gravity to measure masses. What we're going to talk a bit about today is how we actually measure temperatures of stars. And later, in a later lecture, we'll talk a little bit about how we actually measure sizes of stars. So almost all of the information we have about stars comes from measuring the light that we get from stars. In the case of the sun, that's an example where we have a little bit of additional information on top of the light we see. I'll come back to that next time. But most of the information comes from the light we see. And in fact, most of the information comes from specifically the part of the electromagnetic spectrum that's the visible part of the electromagnetic spectrum, what we can see with our eyes. Historically, of course, as we were starting to understand stars, the first telescopes that were developed only looked at visible light. The first telescopes didn't look at X-rays, ultraviolet, or infrared. So our historical understanding of stars built up by using the information in the visible part of the electromagnetic spectrum. So a lot of our understanding of stars in particular and astronomical objects more generally relies on figuring out how light interacts with the stuff, the matter, inside a star or inside a planet or inside a galaxy or a ball of gas. And so it's extremely important in thinking about how we interpret the light we see from astronomical objects to think about how those objects actually interact with light. And really what's happening is it's the light interacting with the atoms and molecules that make up the star. That determines what we actually see. And there's really three fundamental ways that light interacts with matter. One is that matter can emit light. So that's the case of the stars that you see in this image. These stars are all emitting the light that we then subsequently see in this image. Another way that objects interact with light is actually by absorption. So in this image, what you see is background stars, but then there's actually a cloud of gas and dust that is blocking the light from the background stars. So this dark region is a region where none of the background starlight is making its way to us. And so the gas and dust here is absorbing the background starlight, and so we see this dark spot in the image. So emission, absorption are two of the key ways that light interacts with matter. And then the last one is that light actually bounces off of matter. So in this image, you're actually seeing reflection several times over. The light that you see from the trees here is light from the sun that is reflecting off of the leaves of the tree and coming to our eyes. So what we see when we look at trees is actually reflection off of the leaves. And then you're seeing a second reflection. The image of the trees is then reflecting off of the lake and producing a second reflected image. So these three processes, emission, absorption, reflection, really govern a lot of how we interpret the light we see, not only from astronomical objects, but from everyday objects as well. And there's a particular type of emission of light that is critical for understanding astronomical objects. And this is called thermal emission, or the kind of more physicsy name for it is black body emission. And the basic idea is that if you have sufficiently dense gas, solid, or liquid, an object emits light that only depends really on the temperature of the object. The kind of properties of the light that are emitted don't depend on lots of other properties of the object. For instance, it doesn't depend on exactly how much mass there is of the stuff. What really governs the properties of the light that you see is just the temperature. And this is called, again, thermal or blackbody radiation. And the basic idea of the properties of this light are illustrated in this sequence of images. If you have relatively cold objects, then you emit less light overall. and the light is in the redder part of the electromagnetic spectrum. So remember, redder part of the electromagnetic spectrum is kind of infrared. That's longer wavelengths. So cooler objects that emit thermal radiation emit less light, and they emit redder light, longer wavelength electromagnetic radiation. Hotter objects emit more light, and they emit light that is bluer, meaning it's shorter wavelength. Okay? And this intuition, or this fact, really, that hotter objects emit more light and it's bluer, this is actually a little counterintuitive, because if you think about your everyday experience, you go to wash your hands or take a shower, right? The standard convention is that the hot water is labeled red, okay, and the cold water is labeled blue, which is actually the opposite of the right answer from physics. And the reason for this everyday kind of experience or everyday intuition is that cold objects are like ice cubes, which, because of how light reflects and bounces off of ice, looks kind of blue. And so that's why we call cold blue when we think about a faucet. And in everyday experience, a hot burner, which is red, is hot enough to burn your hand. And so it's actually pretty hot by everyday experience. And so we label that faucet red. But in fact, this is actually backwards of the right answer from physics, which is that as objects get hotter, they emit more light, and the light gets bluer and bluer, shorter and shorter wavelength. Okay? And so I can illustrate this a little more kind of quantitatively by showing you a plot of how much light is there as a function of wavelength of light. So this is short wavelength, this is long wavelength. So radio, visible, X-rays, gamma rays, right? Gamma rays and X-rays are very short wavelength light. Radio is very long wavelength light. And then what this movie is going to show you is a plot of how much light there is marching through a hotter and hotter object. What is its thermal emission? And so as the temperature goes up, you see the overall brightness goes up, and the light shifts to shorter and shorter wavelengths. The peak, where most of the light comes out, is at shorter wavelengths when it's hotter. And this is kind of the quantitative version of that general argument I just gave you. So as you go from hundreds of degrees to tens of thousands of degrees to millions of degrees, you go from emitting mostly light in the radio to emitting mostly light in the visible to emitting mostly light in the X-rays. Yep?
So a very hot object still emits all kinds of wavelengths?
So a very hot object does emit a range of wavelengths, as you can see by this curve here, but most of the light that it emits comes out at short wavelengths. Exactly. There's always this distribution. Yep?
So the trio of brightness, temperature, and a shortening wavelength are all directly proportional?
That's right. Exactly. So the combination of brightness, shorter wavelength, and what was your third one? Temperature, yeah, okay. Brightness, the wavelength, and temperature are all intimately connected to each other for this thermal or black body radiation. So let me give you a couple of examples of this. So this is the sun. This is an image of the sun taken with the wavelengths that your eye can see, which is the visible part of the electromagnetic spectrum. And the sun actually looks pretty white. White corresponds to, if you remember your prisms, white corresponds to a range of wavelengths, a fair amount of blue, a fair amount of red, kind of roughly equal amounts of that. And the reason for that is that at 6,000 degrees, which is the surface temperature of the sun, the peak emission is right in the visible part of the electromagnetic spectrum. And that's not a coincidence, of course. The sun formed first, it formed first, and it was emitting in the visible when the first bacteria was evolving to become multicellular, and the first eyes were starting to evolve. And so eyes adapted to see primarily the light produced by the sun, which is in the visible part of the electromagnetic spectrum. There's also these dark regions in this picture. These are called sunspots. So this is now a zoom in of a patch, kind of maybe yay big. So a patch of the surface of the sun. It's a slightly different color scheme, unfortunately, but it shows much more clearly this very, very dark region. And these dark regions are regions that are emitting less visible light. And in this case, they're emitting less visible light because they're colder. So sunspots are regions of the surface of the sun where the temperature is only about 4,000 degrees. Now remember, 4,000 degrees, right, would completely burn you to a crisp. So that's extraordinarily hot by any everyday experience. But it's colder than the typical surface of the sun, which is 6,000 degrees. And so it looks much darker. It looks like there's much less light. There is, in fact, much less visible light emitted from this region because it's cooler. So when you're looking at this picture of the surface of the sun, when you see light and dark, you really are seeing different temperatures. The dark regions are the cooler regions on average. Okay? So room temperature, right, in this room, that's about 70 degrees Fahrenheit, 20 degrees Celsius. And it turns out that at room temperature, thermal emission is in the infrared. So each of us in this room and the walls and the chairs, everything is emitting thermal radiation in the infrared part of the electromagnetic spectrum. The infrared part of the electromagnetic spectrum is not something that you can see with your eyes. The wavelengths of infrared light are too long, and so with your eyes, you don't actually see the thermal radiation produced by everyday objects. But you can go out and get infrared goggles. And with infrared goggles, which are basically cameras that convert infrared light into visible light that you can see with your eyes, you can take pictures of everyday objects in the thermal radiation that they produce. So this is an example. This is a picture of deer taken with infrared goggles. The deer show up as much brighter than the surrounding trees, and the reason for that is that kind of living creatures, which have temperatures of 100 degree Fahrenheit, roughly, right? They're hotter than, say, trees or the ground, typically, and so they look a little bit brighter than everything around them. And likewise, with the infrared goggles, you can see a person's face stand out relative to their surroundings because they're hotter than their surroundings. So we can see the thermal radiation produced by everyday objects if we have a special type of camera, special type of goggles like night vision or infrared goggles. So with our eyes, what do we actually mostly see in everyday experience? If we're not seeing thermal radiation, what are we actually seeing? We're seeing visible light, but where does it come from? It's not thermal radiation. It's sunlight typically reflected off of objects. So most of what we see actually in everyday experience is reflection of sunlight or reflection of light bulbs. The light comes from the sun or from the light bulbs, bounces off of me, goes to your eyes. So that's really fundamentally this process of reflection, not this process of thermal radiation. Yep? Correct. Staring directly at the sun would generally be emission, with perhaps, with a wrinkle that I'll get to in just a second. Yep. Okay. So I'm going to ask you guys a question now. So get out your pieces of paper. So I want you to talk to each other and think about this for a second. What are an example, or possibly more than one example, of actual thermal emission, the emission produced by an object because of its temperature that you experience in everyday life? Is that the light we see from the moon? Is that the blue light we see in the sky? Is that the red sky we see at sunset? Or is that the light from light bulbs? So talk to each other about that for a second, and then we'll take stock and evaluate it. All right, I see some greens. Any other guesses? Don't be steamrolled by the green mafia. Okay, green is the right answer, though. So actually, green is only sort of the right answer. There is a subtlety. Anybody know what the subtlety is? Right, so if you mean the light bulb, the glass around it, it's not the light bulb, it's the tungsten filament. But not all light bulbs these days are actually tungsten filament light bulbs. There are other kinds of light bulbs, which are called, compact fluorescent light bulbs. So this is technically only true for incandescent bulbs, which are the tungsten filaments that get heated up and emit thermal radiation. Fluorescence is a type of emission, but it's not thermal emission. It's emission only at certain wavelengths. And so objects can emit light that isn't thermal radiation, but is instead emission only at very characteristic wavelengths having to do with what the stuff is made of. And we'll come back to that in a second. Yep? Yes, so if your argument the argument that was just given is that, well, the moon is reflecting the thermal emission produced by the sun, and so I'm going to call this thermal emission of the sun. Great answer. I agree. So, I was viewing this as the moon is reflecting the sunlight, but your answer is exactly right. So how do we make sense in particular of these two examples here of blue sky, as in this photograph? Where is this taken? Yosemite Valley, exactly. Or the red sky at sunset? The answer is that this has to do with how light from the sun interacts with the nitrogen and oxygen air molecules in the Earth's atmosphere. And it turns out that blue light, as light from the sun travels and goes through the Earth's atmosphere, blue light is redirected more efficiently than other types of light. So we say that blue light is scattered or bounced around more effectively than other types of light. And so when we look up at the sky, not directly at the sun, what we're seeing is sunlight bouncing off of the air molecules in the Earth's atmosphere. And because the blue light is scattered more effectively by air molecules in the Earth's atmosphere, we preferentially see the sky as looking blue. Yep? Yeah, great question. So the question is, what would the day sky look like on different planets with different atmospheres? We do have a decent understanding because we know the composition. So I think on Mars it's a little redder. Actually, if you go in the Earth, if you've ever been hiking or backpacking at very high altitude, the blue is much darker. It's actually getting almost blacker, and you're starting, if you go, in the space shuttle or SpaceX in the future, you take your little space trip high up, right, you would actually at some point get above the Earth's atmosphere, and you wouldn't really see the sky. You would just see the black, empty space. And so that's why it gets kind of darker blue as you go up in the Earth's atmosphere. Yep?
So oceans appear blue because of the sky, like blue light being scattered more effectively. Is that why?
It's also because I believe, I'm more sure of this actually for ice than water, but I believe it's also true that water does preferentially scatter blue. Charles, do you?
I think the real reason why water looks blue is because it's reflecting blue sky.
Okay, yes.
Water, it's not blue at all, right? It's green.
Yes, good.
Because green preferentially absorbs in the red. You take red out and look at green. So if you're on a dock and you look straight down, the water's greenish in color. It's not blue at all. And that's why when it's all cloudy, it looks steely gray, because it's reflecting what the sky looks like.
Yep, good. Thank you. Okay, so this explains the blue sky, and the basic mechanism explains why sunsets are red. It's the same idea. At sunset, we're looking more directly towards the sun in this type of image, or if you look at a sunset. What's happening is the blue light is still preferentially being scattered, but now it's the blue light that is going away from the direction we're looking, and what's left, what makes it through, is preferentially the redder light, not the bluer light, and that's why sunsets preferentially look red. And so these examples from our everyday experience are really governed by the reflection or scattering of sunlight off of air molecules. Yep?
Is it like a like molecule or some sort of compound that causes?
So it's a process. The question is it a specific molecule or atom? It's a process called Rayleigh scattering that works really on both the nitrogen and oxygen molecules in the atmosphere. So it's a similar process. Okay. So the situation when you look up at stars is actually rather different. When we look at stars, the color that we see is actually a reasonable indication of the temperature of the star. Unlike in everyday experience, for instance, where the color tells us more about how light is being reflected off of objects, when we look at stars, the color really is telling us something about temperature. Redder stuff is generally cooler. Bluer and whiter stuff is generally hotter. The slight caveat that we're not really going to go into is that as light goes through gas and dust that fills the space between stars, different wavelengths of light are affected more by dust and gas that fills the space between stars. So that can actually change the color of light in a way that's analogous to what we just talked about for the Earth's atmosphere. But to a much better approximation than in everyday experience, color is a useful proxy for temperature when we look at starlight. What that means is that we can actually figure out the surface temperature of stars just by looking at whether they emit most of their light in the redder part of the electromagnetic spectrum or the bluer part of the electromagnetic spectrum. So that's one way that we use the light that we see from stars to infer the intrinsic properties of stars. In this case, the temperature at the surface of the star. And I should emphasize the temperature at the surface of a star is very, very different from the temperature in the interior of the star. It's much, much hotter in the deep interior, and that's something we'll talk a bit more about next lecture. So, in addition to the light from stars encoding information about the temperature of stars, it also encodes a lot more information. And one of the most important of those has to do with the fact that as light moves through a gas that's composed of atoms or molecules, those atoms or molecules absorb the light at very specific, special, unique wavelengths. So what do I mean by that? What I mean is that each atom or each molecule absorbs the light at distinct, unique wavelengths. And the pattern of what wavelengths the light gets absorbed at is really unique to the atom or molecule. That's the sense in which it's kind of a fingerprint, that if you look at the pattern of what wavelengths of light are being absorbed as light propagates through some gas, you can use the absorption pattern to figure out what atoms or molecules make up that stuff. And so the kind of visual impression of this that you should have is illustrated in two different ways in this image. So this is kind of brightness of light as a function of wavelength. Redder light is to the right, bluer light is to the left. And this shows the absorption produced by hydrogen gas. So you have light which is passing through some hydrogen gas, and the hydrogen gas is absorbing the light. So it looks darker, there's less light coming through at very specific wavelengths. And the wavelengths where there's less light, where there's more absorption, less light, okay, those wavelengths are specific and unique to hydrogen. So if you see this pattern of absorption, you know that that light has passed through some hydrogen gas. If you see a different pattern of absorption, you can figure out that the light has passed through oxygen molecules or oxygen atoms or iron atoms. So you can use the pattern of absorption to figure out the composition of the stuff that the light is passing through. And so the way you should think about this in the context of a star or a planet like Jupiter is that light that is produced deeper in the hot interior, as it passes through the outer atmosphere of the star, some of the light is absorbed in the outer atmosphere of the star, and we can use the pattern of absorption that we measure when we actually look at the light at different wavelengths coming from stars. We can use the pattern of absorption to figure out what the stars are actually made of, what the composition of the star is. Is it this pattern of absorption, so it's mostly hydrogen, or is it a different pattern of absorption, so it's mostly iron or something else? Okay. So that's how we use the light from stars to not only figure out temperature, but to figure out more detailed properties like what stars are actually made of. Hydrogen, helium, iron, oxygen, you name it. We use this kind of fingerprint of absorption. All right? Does that make sense? Okay. So how do we actually do this? Well, what you do is you take the light from a star, you put it through a prism, and as you probably remember from high school physics, the prism breaks, say, white light up into the range of wavelengths that white visible light is made of. Red, orange, yellow, green, blue, violet, etc. And then you can look at how much red is there, how much orange is there, how much yellow is there. And you can look at the different colors or the different wavelengths of light separately and actually figure out then, is there more absorption in the red, in the orange, in the green, in the blue? And that'll tell you about the composition. I want to show you, since this is at least partially an astronomy class, at least one telescope. And in particular to emphasize to you that a modern prism that we actually use on a modern telescope is not like this little thing of glass that's shaped like a pyramid. So a modern prism is about this big compared to a human, right? Modern instruments that actually take light and break it up into many different wavelengths are actually extraordinarily complicated. There are these really technological marvels. So this is an example. This is a instrument on the Keck telescope. This is this telescope in Hawaii that the University of California and Caltech operate, that breaks light into many, many different wavelengths and that we use to figure out what stars and galaxies, et cetera, are actually made of. So when this was first done in the 19th century, the end of the 19th century, beginning of the 20th century, the result was quite astonishing. The result that people inferred when they measured what stars were made of is that stars were actually made of very, very different things than the Earth. And in particular, stars are made mostly of hydrogen and helium. So when you look at the light from a star, what you infer is that most of the mass of a star is hydrogen. There's a little bit, about 25% of the mass of a star is helium, and a few percent is everything else. Everything else, oxygen, carbon, iron, gold, you name it, is just a trace amount, a few percent of the mass of a typical star. And this turns out to be an extraordinarily important clue to our origins. The fact that stars, and that in fact the gas between stars, the building blocks of stars and planets, are mostly hydrogen and helium, turns out to be one of the big clues to our origin and the beginning of the universe in the Big Bang, as we'll talk about later in the class. And remember, this really is fundamentally different than the composition of the Earth. The Earth is mostly made of iron, silicon, oxygen, magnesium, and the stuff that the sun is made of, hydrogen and helium, right, is kind of other for the Earth. And we sort of understand this based on our understanding of how planets form. Remember, planets form starting with small rocks that collide together and build bigger and bigger rocks. And so planets like the Earth are made from really the stuff that rocks are made of. And so that's the silicon and iron, for example. And in the case of the Earth is not big enough. It doesn't have enough gravity to hold on to a lot of hydrogen and helium. Unlike Jupiter, Jupiter started kind of like the Earth, mostly iron and oxygen and silicon, but it was able to gobble up a lot of surrounding hydrogen and helium. Yep?
How are they able to take all the elements in the light and lay them out?
Yeah, so it's tricky. So the question is really, how can you figure out, given some pattern of absorption, which elements there are? And the reason you can do it is, again, that the wavelength that the absorption happens at is really unique to each element, oxygen, iron, whatever. And you have many of these lines from each element. And so there's enough information to figure out what lines are produced by what elements. But it's not it's a complicated exercise to do because you have to kind of figure out which lines go with which element. But there's enough information to do it. So, yeah, good question. Okay. So again, this is what stars are made of. This is what the Earth is made of. And humans, remember, we're actually made of something yet different. Humans are made of mostly water, so we're made of mostly hydrogen and oxygen. There's iron in our blood. There's carbon for reasons that we'll see later. Carbon is one of the kind of most important molecules for actually performing chemistry and hence for performing kind of biological and chemical reactions. But the thing to notice, right, is that life, humans and other forms of life, actually make use of only a certain set of the elements that are at our disposal on Earth. The carbon and water in particular are the elements that turn out to be particularly useful for life. And so we are made of elements that are different from the Earth, and the Earth itself is made of elements that are different from typical astronomical objects like stars or the gas between stars. Okay. So the last thing I want to emphasize about our understanding of stars is that when we gather together all of the properties of stars that we can measure, what they're made of, what their temperature is, what their luminosity is, how bright they are, how much light they're putting out, what the mass of a star is, what the radius of a star is. What astronomers do is exactly what biologists or geologists do. We try to classify stars. We try to say what kind of groups do stars come in, what properties of stars are the most important in determining other properties of stars. So we organize stars. And the way we organize stars is in a diagram that's illustrated here that's called the Hertzsprung-Russell or HR diagram. It's named after the two people who kind of pioneered this line of work. And what this is a plot of the luminosity or the power, the watts, produced by a star in units of the luminosity of the sun. So stars that emit huge amounts of light are up here. Stars that emit very small amounts of light are down here. It's a plot of luminosity versus the surface temperature of a star. And astronomers have this horribly weird convention of actually plotting stars that are hotter to the left in this diagram. You're used to kind of the bigger numbers showing up on the right-hand side of a plot, and the way that astronomers do this plot is hotter stars with hotter surfaces, show up on the left, cooler stars over here. And so what you can do is you can ask, of all the stars in the night sky, if you put them on this diagram of luminosity and temperature, where do they lie? And you might, if you didn't know anything, you might think that stars could have any surface temperature and any possible brightness. And that turns out not to be true. That stars actually obey a remarkable kind of regularity in that most stars, most of the time, lie along this band that is called the main sequence. And that band has the following property, that stars that are hotter, that have hotter surfaces, also emit much more light. And this should kind of make sense because this is a property of objects that emit thermal radiation that we just talked about. Hotter emits more light. Okay? And stars have this property that the ones that are hotter emit substantially more light. The sun has a surface temperature of about 6,000 degrees. It emits 1 luminosity of the sun. Stars that have surface temperatures of 40,000 degrees emit more like 1,000,000 times the luminosity of the sun. And perhaps the more interesting thing is not only is there this relationship between luminosity and temperature, but every other property of a star, its mass, its radius, its density, follows this amazing regularity. The stars that are very bright and very hot turn out to be the stars that are more massive, and the stars that are physically bigger, have larger radii. The stars that are cool and faint turn out to be very low mass and very small. And so the remarkable conclusion when we synthesize our observations of stars is that really, if you know one property of a star, which is conventionally taken to be its mass, if you know the mass of a star, you can really figure out the entire life of a star. You can figure out, given its age, you can figure out how big it is, what its radius is, how bright it is, how hot it is. So there's this astonishing regularity in the properties of stars that really the mass of a star determines its destiny and its fate. Its kind of entire history of how bright it is, how big it is, how hot it is determined by the mass of the star. And we will understand in a few lectures that this amazing regularity of stars is a consequence of really nuclear fusion in stars. And this astonishing simplicity of stars is really different than the biological world. In the biological world, you have objects that have similar sizes or similar masses that have completely different biologies, that might undergo photosynthesis, or they might be like Tyrannosaurus rex, where they, are carnivores. And so objects of the same size can have completely different biologies, kind of chemical interactions with their surroundings. In astronomy, we have this extraordinary simplicity of the fundamental objects, where once we know the mass, we kind of know everything else about the properties of stars. Okay. Any questions about that? Okay. So what I'm going to do now is I'm going to turn to talk a little bit about what actually powers the light that we see from stars and why this was such a puzzle, in particular in the late 1800s. And that puzzle is actually an important illustration of how science functions and turns out to be a very important clue about the properties of stars and the kind of functioning of the Earth and the Sun. And the story starts with the recognition that if every object that has a temperature emits this thermal radiation, so it emits light, the amount of light emits depends on the temperature it has. If that object doesn't have any internal way of producing energy to compensate for the light that's leaving its surface, then it's going to slowly cool down in time. And you're very familiar with this in everyday experience. You start a fire, it starts off really hot. As the wood burns, it cools down, and eventually you're left with ashes after you've gone through all of the energy that's available burning wood to ashes. Or lava coming out of a volcano starts off extraordinarily hot as kind of liquid magma, and as it cools in time, it cools and solidifies and the temperature drops. So this idea that things cool, and remember, as they cool, they emit less light, so they kind of cool and fade away as time goes on. So to understand this a little bit better, this cooling down and fading away, we have to talk about what temperature really means to a physicist. And so I'm going to explain to you briefly the kind of idea of temperature that somebody like me as a physicist thinks about. And the way we think about temperature is that temperature is another way of talking about the energy of motion. And in particular, so you're familiar with the idea that there can be energy that objects have because they're moving. A car that's moving has a lot of energy. If it slams into a wall, the energy of its motion goes into crumpling the car and heating it up, and maybe it bursts into flames, right? That's converting the energy of motion into another kind of energy, heat in that case. Temperature is, in fact, simply another example of energy of motion. And in particular, temperature is an indication of the motion of the atoms or molecules that make up an object. So when you say that an object is hot, has a high temperature, What that really means at a basic physics microscopic level is that the atoms or molecules that make up that object are moving around really fast. So higher temperatures mean that the atoms or molecules are moving faster. They have more energy of motion. Lower temperatures means that the atoms or molecules are moving more slowly, more lethargically. There's less energy of motion. And similarly, it turns out that atoms at a given temperature, atoms that weigh more, move more slowly. So cooler temperatures or more massive atoms or molecules correspond to moving more slowly. Moving more rapidly corresponds to higher temperatures or lower masses. And this is really the kind of fundamental physics understanding of temperature. Temperature is a way of talking about the energy of motion of atoms or molecules, and it has these properties that temperature is really related to how fast atoms or molecules are moving around. So that's the kind of physics idea of atoms or molecules. And so this raises an interesting question, which is that as you go to lower temperatures, things move more slowly. So what is the lowest temperature that things can actually get to as they move slower and slower and slower? So we have some experience of cold temperatures in everyday experience, not really in California, unless you go to the Sierras or Mount Rainier or something in the winter. But, in Chicago last year, there was the polar vortex. I was unlucky enough to be there. Or you can go to Siberia in the winter, and it's really cold. And just to give you an example of the coldest kinds of situations that we experience in everyday life. So this is an example. This is cold by everyday experience standards, but it's actually not cold by astronomical or physics standards. Cold by astronomical or physics standards is when the atoms or molecules stop moving. This is the coldest things can get, when the atoms or molecules that make up the object are no longer moving around. Okay, there's a caveat here. If you're interested in physics, you'll learn about this caveat later. Otherwise, ignore it. You don't need to know that. So, the coldest things can get is when the atoms or molecules stop moving. So how cold is that? Well, how cold that is depends on what temperature unit you're using. So in Fahrenheit, this is negative 460 degrees Fahrenheit, okay? Not negative 13, negative 460. In centigrade, that temperature is minus 273 degrees centigrade. And in Kelvin, which is the temperature scale that's used in physics and astronomy, the temperature when atoms and molecules stop moving is 0. That's, in fact, how we define 0 temperature in the temperature scale used in physics and astronomy is when atoms and molecules stop moving. So centigrade and Fahrenheit are defined differently, right? In centigrade, water freezes at 0, water boils at 100. In Fahrenheit, water freezes at 32, water boils at 212. And so the different temperature scales have different ways of defining temperature. And in Fahrenheit, that definition is really 0 temperature is the temperature when atoms and molecules stop moving. And so this temperature scale, this is actually the most convenient temperature scale when you start talking about really cold things, because then you don't have to worry about whether it's minus 268 point whatever, right? It's just 4 or 5. It's measured relative to 0. And so this is particularly convenient at very low temperatures. Yep.
At that temperature, does all kinetic energy become potential energy?
So the question is, at that temperature, does all kinetic energy become potential energy? And I guess the way I would say it is that at zero temperature, there is no kinetic energy. There could still be potential energy. Okay? And again, the caveat is that there could be kinetic energy in quantum mechanics. Again, that's just for people who are interested. But yeah, so I would say at zero temperature, there's no kinetic energy, except for the footnote, and there could still be potential energy. Any other questions? So we haven't really talked about the temperature that fills the space between stars. So just to give you a feel, that temperature is actually about 30 Kelvin. So in this image, this kind of pillars of creation image taken by the Hubble Space Telescope, the gas that fills the space between stars where new planets and new stars are forming is actually pretty cold by the standards of everyday experience. Negative 240 centigrade, right? About 30 degrees Kelvin. Okay. So I want to ask you another question. Now that we better understand how to describe temperature, what are actually the temperature of the coldest places that we know of in the universe? So take the space not between stars, but actually the space between galaxies, where there's extraordinarily little material, as in this is this Hubble deep field. What is the temperature of the space between galaxies? The coldest places in the universe. Is it 0 degrees Kelvin, 3 degrees Kelvin, 0 degrees centigrade, 10 degrees Kelvin? So talk about that for a second, and then we'll reconvene. So, okay, go ahead and raise up your guesses. Okay. A lot of blues. Good. So which of the answers should you kind of immediately rule out? Yeah, 0 degrees centigrade, because we just talked about negative 243 degrees centigrade. So 0 degrees centigrade, that's just making sure you're on your toes about units. Good. So the answer turns out to be 2.73. Which is about 3. That fact that the coldest places in the universe have temperatures of about 2.73 degrees Kelvin or 3 degrees Kelvin is the single most important clue to the Big Bang model for the origin of the universe. That is called the cosmic microwave background radiation, that we will spend a fair amount of time understanding why there is stuff, in this case light, that fills the entire universe at this temperature of 2.73 degrees, and why that is such a key clue to the Big Bang. We'll spend a fair amount of time talking about that in a few weeks. So this is really the most important quantitative clue to our origins in the sense of the universe as a whole. Okay, so we now have all of the ingredients to really pose the fundamental problem that was raised by the mere existence of the Earth and the Sun in the late 1800s. And the problem was recognized and quantified by this very austere-looking person who looks kind of like, a Russian writer. He's actually not. This is William Thomson or Lord Kelvin. And what he realized, so he's one of the inventors, so Kelvin temperature scale, not a coincidence. He's one of the originators of our understanding of thermodynamics, which is kind of the theory of hot stuff, the theory of temperature, really. He is the really founder of that understanding of physics. And what he realized, it was just absolutely brilliant. What he realized was that there was no energy source known in the 1800s that could explain the heat produced leaving the surface of the Earth and the Sun. The Sun is losing energy because it has a temperature, and so it's radiating heat away. And so it should slowly be cooling down and fading away. And the same thing with the Earth. The Earth reflects light from the Sun, but the Earth also has some heat in its interior, which it is radiating into space, and it should cool down. And what he calculated, based on understanding of the laws of physics at the time, was that the Sun should be about 30 million years old, and the Earth, it was a harder calculation, and I can go into why if people are interested, maybe afterwards. But the Earth, he calculated, should be about 20 to 30 million years old. And,
20 to 30 or 20 to 300?
sorry, 20 to 300. Thank you. I misspoke. 20 to 300. So this was a harder calculation, so he was pretty happy. They kind of agreed. Earth and Sun should have about the same age. And he was a physicist, and I'll be honest, we physicists tend to be a little arrogant and think that we're right. And so there was a big debate, actually, that developed between Kelvin and Darwin, the biologist, Lyell, the geologist, about what the actual age of the solar system was. Kelvin advocated, based on the understanding that things fade away slowly as they emit light, that the Earth and the Sun could only be maybe 30 or 50 million years old. And as Charles will now describe to you, this was really inconsistent with the understanding of biology or geology at the time. Maybe it's easiest to just hold.
Yeah, maybe it is. So when we come to the, is that on?
Yeah, it's on.
That's louder? Yeah, that's on. So when we come to the issue of the age of the Earth, prior to Lord Kelvin and prior to Darwin and Lyell and also James Hutton, that you should be reading about in the Bryson chapters for this week, the only information we had on the age of the Earth and the universe was from the Bible. And the estimate was that the age of the Earth was about 6,000 years old, formed in 4004 BC, 23rd of October, 9 o'clock in the morning to be precise, which was the calculation that was in the standard calculation. And then the fellow who founded modern geology, James Hutton, a Scot in the late 1700s, started to recognize that if you extrapolate from processes, rates of processes that you know, rates of formation of soil, where we have a measure of how fast soil forms, and look at vast thicknesses of soils in England, the Earth had to be an awful lot longer than 6,000 years old. And so we came up with a phrase that caused enormous friction with Kelvin, and that is that the age was so old, the Earth was so old, there was no vestige of a beginning, no vestige of an end. So it gave a sense of this eternally running machine. He was a deist, and he believed that God had made the world for man, and of course thus it would have no beginning or end. And this flew in the face of Lord Kelvin, who founded thermodynamics, that says that things run down. And so there was this incredible debate between them. Lyell picked up Hutton, who wrote dreadfully. And then Darwin followed in the geologist's footsteps, as we will see in a lecture or two from now. So Darwin in particular, but also Lyell, felt that these numbers, even though they're vast, were much too shallow, 30 million years, 100 million years. And part of it is that Darwin felt that the succession of species seen in the fossil record should be much, much older than that. Though I really honestly don't know how he got an absolute number, because we don't really know without a timescale how long species last. But the geologists in particular started to try to calculate the age of the Earth by, say, looking at how much sediment it accumulated to make mountains. and you can measure the rate at which sediment is deposited in rivers and then calculate how long rivers must be depositing sediment to get thicknesses of sediment to produce Mount Everest or all the rocks of England, which are all tilted on side. And they were getting numbers of hundreds of millions of years, some of them out to billions of years, which flew in the face of Lord Kelvin's estimates of 30 million to 100 million. So there's incredibly cantankerous debate, but driven in part by Kelvin's insistence that the world has to be running down, and Lyell and Darwin's sort of lack of acknowledgement of that. And so then, of course, what happened was the discovery of atomic nuclei and radioactivity, which Eliot's about to speak upon, which indicated that there was a source of energy for the sun and inside the earth that accounted for the lack of the rate of the cooling. If you believe that the sun's energy and the earth's heat formed at the time of formation, all the matter collapses, the gravitational heat melts the planet Earth, forming the core, heats the sun, and after that it's just slowly heat leaking away. You get the shallow estimates of Kelvin. But if there's a source of heat inside the planet, inside the sun, continually operating, then you can get much longer durations. And so Kelvin's number was shown out to be quite seriously wrong. So the important lessons about science: theories are provisional when assumptions are uncertain, and one of the tricks is knowing when your assumptions are uncertain. And as scientists, we tend not to be very good at that. Because you take an assumption, you rely on it, it becomes a foundation of your thought, and it's hard to think both about your foundations and where your foundation is trying to get you to. Kelvin's reasoning was right, that the sun and the earth are running down, but his assumptions about the nature of that were quite wrong because he did not know about the internal source. And in the end, then, most participants finish up being at least partially right, which is not uncommon when you get cantankerous debates. It's very rare that one is just plain wrong. It's usually they grab different parts of the truth and we can't get them to match. So the Earth is running down, but the Earth is so incredibly old that for hundreds of millions of years it is pretty much in the same state continuously. Just like we can't see the continents move on our timescales, so you can't feel the Earth cooling down for tens or hundreds of millions of years. And so that was sort of the essence of the debate with the age of the Earth and the Sun. And now what we need to work out is where does that energy come from?
Okay, so that takes us to the last part of today's lecture, which will then lead into Thursday's lecture, which is to start our understanding of the nature of matter, and that will lead into our understanding of fusion and the generation of energy inside stars. So to remind you, we organize our thinking about matter, and in particular atoms or elements, using the periodic table. And in particular, the periodic table is an organization of matter based on how heavy different atoms are. It goes from the lightest elements to heavier and heavier elements as you go through the periodic table. And the different columns here are actually organized based on chemical reactivity, how different elements participate in chemical reactions. So this is kind of a critical understanding of Mendeleev in the late 1800s, was that there was this organization of matter which could tell us how different elements would participate in chemical reactions. And we'll come back to this when we talk about the fact that life as we know it is carbon-based. And in science fiction, you'll often hear people talk about silicon-based life forms. That may or may not be science fiction. As far as we know, it is. But the reason people invoke that is that's the same column in the periodic table. So there's similar chemical reactivity between carbon and silicon. And so just like carbon is good for life, maybe silicon is good for life. Some of these elements actually are not found generally in nature. They're just human-made. So I've put them in red boxes here, are the ones that are human-made. In particular, the very, very heavy elements, unanillium, one of my favorites, and some of these other ones are human-made. Two examples that may be of particular interest to you: berkelium, which is element 97, and californium, element 98. So 97, 98 in the periodic table are human-made. In fact, the reason they have they're named after Berkeley and after California is that they were created here at the Lawrence Berkeley National Lab. So LBNL, which is a national laboratory for science funded by the Department of Energy, really initiated a lot of the early experimental work creating new elements, so kind of alchemy, creating out of thin air almost new elements in the periodic table. Yep? Yeah, seaborgium. So I didn't put all of the ones we made here. I put a few examples. There's Lawrencium, Lawrence Hall of Science, Lawrence Livermore National Laboratory, exactly. Seaborgium, Glenn Seaborg. I forget exactly how many. Element 115 was confirmed here. Yeah, so there are actually a number that were made here. That's exactly right. Okay. So let's just briefly talk a little bit about what matter actually is at its microscopic heart. The answer is empty space. Most of matter is nothing. It consists of a very, very small atomic nucleus. The atomic nucleus has a size of about 10 to the minus 15 meters, and it has a positive charge. The nucleus is surrounded by swarms of electrons. The electrons are constantly swirling around the atomic nucleus. The electrons are negatively charged. The nucleus is positively charged. And it's the attractive electric force between the negatively charged electron and the positively charged nucleus that holds the atom together. The electron is typically at a distance of about 10 to the minus 10 meters from the nucleus. As far as we know, the electron is this tiny little thing, much smaller than 10 to the minus 15 meters. So as far as we know, the electron has no internal structure or size. So that's what I mean by atoms are mostly empty space. There's this nucleus, which is 10 to the minus 15 meters big. And then you have to go out 5 orders of magnitude, 100,000 times further out, and you find this swarm of electrons orbiting around the nucleus. Those are the fundamental building blocks of matter and elements in the periodic table. The nucleus, we now know, is actually itself made of other building blocks. In particular, the nucleus is made of positively charged protons and neutrons that have no charge, neutral. Neutrons neutral. Okay. And it's the positively charged protons that give the nucleus its positive charge. So the nucleus has a positive charge because it consists of positively charged protons and neutral neutrons, so it has a net positive charge. Now, you might think that if the nucleus consists of neutrons and protons, then the electric force inside the nucleus is trying to blow the nucleus apart. Like charges repel, so all the positively charged protons inside the nucleus are kind of pushing away from each other, trying to destroy the nucleus and blow it apart. What holds the nucleus together is another one of the fundamental forces of nature called the strong nuclear force. It's the strong nuclear force between protons and neutrons that holds the nucleus together in spite of the electric repulsion of the protons. And we're not going to go into this, but we now know that protons and neutrons themselves are made of even more fundamental building blocks that are called quarks. As far as we know, quarks are not themselves made of even more fundamental building blocks, but There are theories, string theory you may have heard of. There are ideas that even quarks and even electrons are made of even more fundamental building blocks. So in the periodic table, when we talk about the different elements, what really defines an element to be an element, what makes hydrogen hydrogen, what makes zinc zinc, what makes gold gold, is the number of protons in the nucleus. A given element with a certain number of protons can have different number of neutrons, and those are called isotopes. So there are different kinds of carbon, the same element, because it has the same number of protons, but it has different number of neutrons. So there's carbon-12 and carbon-14, which have the same number of protons but different numbers of neutrons. And we call that an isotope. Same number of protons, different number of neutrons is an isotope. So I already said that the periodic table is particularly useful because it kind of organizes our thinking about chemistry. And in particular, what chemistry really is changes in the configuration of all those electrons swarming around the nucleus of atoms. The elements, during chemical reactions, the elements themselves do not change because the elements are really defined by the number of protons in the nucleus, and the nucleus does not change in chemical reactions. Chemical reactions are changes in how these electrons around the atoms or the molecules are distributed. And so burning fire, photosynthesis, chemical weathering, and the carbon cycle are all examples of critical chemical reactions to this course, right? Fire and the origin of humans. Photosynthesis, chemical weathering, and the carbon cycle that we'll talk about. These are all examples of rearranging the electrons around atoms, but not changing the basic fundamental nature of elements. Yep? Yes. Correct. So it is possible to change the fundamental nature of elements from one kind to another. And there are two basic ways that this happens. One is fusion. You combine two light elements to form a heavy element. That process of combining light elements to form heavy elements, that is the basic energy source inside the sun. And that fundamentally alters the nature of the nucleus or the nature of the atoms. You literally change hydrogen and make it helium. This is alchemy in the sense that, the ancients were looking for, literally turning lead into gold, changing one element into another. This is an example of a fusion experiment trying to perform fusion on Earth to create clean power as an energy source. The other type of changing elements that we know of, changes in nuclei, is called fission or radioactive decay. That's breaking one heavy element up into two lighter elements. So fusion, you build heavier things from small things. Fission or radioactive decay, heavy things break down into small things. And fission is, in fact, a key energy source inside the Earth. And when you think of a nuclear reactor, nuclear reactors operate on the process of fission, not fusion. This is actually the fission reactor outside San Luis Obispo, which is a little bit north of Santa Barbara. And so what we will talk about next time is how to understand the way stars undergo fusion to generate energy and build up the heavier elements in the periodic table.